Cool. Unfortunately, I cannot see any reactions. There's this full screen on my monitor here. So I'll look at the chat and questions and stuff, everything later. Uh, Faiz, if I'm going too fast or anything, just unmute yourself or if I get disconnected or something, just unmute yourself and call it out.
Okay.
Okay, cool. Okay, hi. Thank you for showing up on a Saturday afternoon on a weekend. I'm going to be talking about something which is one of my favorite topics, uh, but usually is not a favorite topic for most engineers, which is software estimation, which is doing this exercise of trying to figure out how much time or how much effort will it be to fix something, to build something, so that you can talk to a bunch of stakeholders and understand if the something should be done or not, right? This is a fairly complicated topic, as I realized when I researched into this. And a lot of the charts that are in this presentation come from this book called Software Estimation by Steve McConnell. It was published in 2006 by Microsoft Press. You can get yourself a copy if you um, feel like this is something that you want to go into a little bit more detail. But the book is, I will warn you that the book is not interesting at all. It's actually a really boring book, right? Cool. So my name is Pratul. I had engineering at Obvious. We are an agency based out of Bangalore. And we do product design, we do engineering. I'm sure you've used some of our apps that we worked on over the couple of years that we've been around. Okay, so what is an estimate? Okay, let's start off with that. Um, it's surprising because I'm sure a lot of you are thinking in your head that, yeah, of course, I know what an estimate is. But let's try and break this down a little bit. Right? An estimate is how much time will it take to finish all these things, which is it is something that has a certain degree of probability attached to it, right? So an answer of an estimate, a question which requires an estimate would be, let's drive from one end of the city to another. Right? And depending on what time of the day you start and depending on what mode of transport you're using, this is going to take a variable amount of time, right? So someone will probably say, so hey, how long do you think it'll take me to drive from one end of the city to another? And you might say, I don't know, 45 to 65 minutes. Now, now that is an estimate, right? And it's important because estimates always have a probability attached to them, right? Um, and this is a very important point to bear in mind, and this is something that's going to get repeated over and over in the presentation. So bear this in mind, right? What is not an estimate is a target, right? And a lot of times, teams and management and engineers confuse targets and estimate. And sometimes when people are discussing a target, they think of it as an estimate. Or sometimes when what management is actually looking for is an estimate, teams think of them as, engineers think of them as targets. So what is a target? A target is when you have a situation where here are a bunch of things that you have to get done by X, right? For example, a train that leaves at 4:40 p.m. Now, this is a target because there is no way that you will be successful if you do not actually meet the timelines, right? If you don't get those things done by X, or if you don't reach the railway station by 4:40 p.m. or before 4:40 p.m., you're not going to take the train and you are unsuccessful in your attempt. So one of the first questions that I want to put in your head as you that's something that you take away from this talk, right? And as you go back into doing engineering, is are you chasing a target or an estimate? Right? And this is something that you have to think about and something that you should bear in mind because the answer to this question changes the conversation that you're going to have with everyone else. Because if you're chasing a target, then the way you go about it is very different from a situation where you're actually being asked for an estimate, right? Pressure and bad estimates, right? What is pressure? Pressure is pressure, and bad estimates are the result of pressure. This is something that all of us as engineers have thought about many times. I have been guilty of this as well. Okay, I mean, here's a bunch of things that I have to do. Yeah, it looks like it's a lot of work, but I'm sure I can do this in 3 days. But I don't think it'll take me more than 3 days. Right? And all of us have behaved like this in this fashion as engineers, right? Uh, And that doesn't help at all because you're putting yourself in an unreasonable situation. Right? And this is something that I have done personally myself over and over again. And it took a lot of practice to break out of this mindset that there are no prizes for getting there fast. No one gives you a prize that, oh wow, I asked this engineer to do something and they did it in just 3 days, right? No one actually cares if you do it in 3 days or 2 days or 4 hours or whatever. What people actually care about is, are you able to set a reasonable timeline? Are you able to deliver on an estimate that you provide? If you come up with an estimate of 3 days and you deliver on that 3 day estimate, people are happy, right? But because we estimate so poorly and because we end up internalizing this pressure that, oh my God, I as an engineer, I can't say 3 days. I think I can do this in 2 days, right? There's this mentality that we have that let's build pressure into ourselves. And that doesn't help us at all because of two different reasons. The first one is called the Parkinson's law, which is that work will expand to fill all available time, right? Which means that if teams have a lot of extra time, more work will magically get created. And I'm sure if you think about this, you probably felt this in your work at some point, which is that uh, if you have something that you know you can finish in 5 days and management gives you 10 days to do it, it's not you'll finish it in 5 days and the rest of the 5 days you're going to sit empty. You are actually going to end up doing something for the day 6, day 7, day 8, and you realize that after day 10 that you've actually done enough work that it actually filled all 10 days. And this is what Parkinson's law talks about, which is that teams automatically kind of adjust to the amount of time that they have. And unfortunately, what happens as a result of Parkinson's law is that management will always try to squeeze an estimate gives them. So if you say that I think I can do this in 10 days, your manager is going to tell you that, you know what, can you do this in 8 days? Or if you say 6 days, the manager is going to ask you to do it in 4 days, right? And that one of the big reasons why that is the case is because management is trying to fight Parkinson's law. They're trying to actually compress the amount of time that you have to accomplish a certain task so that you're able to, so that Parkinson's law gets defeated, right? The other law is what is called the board-rack student syndrome, which is again something that all of us, I'm sure, have experienced while educating ourselves. Given lots of time, students will delay studying until the last possible moment. This is something that is very happily applicable to developers as well, which is that developers will procrastinate until very late in the project, and then suddenly the timeline is too close, and then we will rush towards the end, and we will not complete things on time, and suddenly things are breaking left, right, and center, etc., etc. Right? This is also applicable to another set of people, which is people who are giving talks at conferences, and you see this with speakers all the time, which is that speakers are preparing their slides at the last moment. So many famous speakers have talked about how they've finished their slides and improved their slides on a flight to a conference itself, right? Uh, and this student syndrome is actually has nothing to do with students or developers or conference speakers. It is a reflection of us as human beings and the way human nature works. And the only way to get around the cold rack student syndrome is to actively work towards it, to recognize it, and then to try and avoid it by knowing that it is something that you exhibit. However, what is important to know is that underestimation is worse than overestimation. Right? So let's say you have a task that will take you 4 days. If you say 3 days versus if you say 5 days, 3 days is much worse than saying 5 days. Because if you are going to underestimate, you have a statistically reduced chance of completing that task on time, right? And I'm going to talk about this a little more in the rest of the talk, but remember this bit, right? Which is that it's statistically reduced chance of on-time completion if you actually underestimate. And the reason that is the case is because engineers are too optimistic already, right? When as engineers, when we are asked to give an estimate for something, we are already crunching the numbers in our mind. In that 3 seconds that we take to actually come back with an estimate, we've actually already worked through all the scenarios in our head. We think that we've already figured everything out, and then we try to kind of shorten it to make ourselves look that we look at me, I'm such a great engineer, and then present a number which is already way too optimistic. Right? I'll show you a scary looking chart afterwards. But remember this bit, statistically reduced chance of on-time completion if you underestimate versus overestimate, right? What are the what are other side effects of bad estimates? Right? The other side effects of bad estimate, one of the big ones, which we recognize after we've done bad estimation, is a poor technical foundation, which is worse for us in the long run. Because you're rushing now to complete things, you've defeated a bunch of deadlines. You know that people are pissed. You know your team members are tired, right? It is. It also results in teams showing unproductive and emotionally draining behaviors, and these behaviors are something that we are again very familiar with. You will end up having more status meetings because suddenly now everyone in the team wants to know what's actually happening. Every day, people want to know what got done yesterday. You'll be forced to do frequent re-estimation because people will suddenly come up to you and say, "Hey, last week you said it'll take you 2 weeks more. It's been 1 week. How much time will it take you to do now?" Right? And there's this constant pressure of conversation. Uh, People who are customer facing are going to force teams to provide interim releases of the software because customers have to be shown something. Can you give us an alpha build? Can you give us a beta build? Why is this feature not working in the beta build, etc., etc., right? Which means you'll have more meetings to cut scope. Things are getting out of hand. Let's get into a meeting. Let's look at our Jira board and see if we can remove some stories. And all of this means that as engineers, you're constantly now hacking together a bunch of different pieces of software. And obviously, those hacks will result in some bugs that only happen towards the very end of the project when you really just want to get over with it, right? And this is a mess. This is a complete mess, and nobody wants to actually deal with this. But unfortunately, poor estimation leads to these side effects. And it's not just a matter of at that time teams not performing well. It is also not a question just of people being emotionally drained. It is at that point an overall systemic failure because software that was supposed to reach the user at a certain point in time, unfortunately, did not reach the user, right? Now, remember that time a couple of minutes ago, I said that there's a statistically reduced chance of on-time completion. Let's look at this as a slightly scary slide, okay? I'm going to bring up my marker here and explain this a little better. What this is showing is what happens when you underestimate versus what happens when you overestimate, right? Which is that this point here is the point where your estimate and your effort are exactly accurate. You knew exactly how much your estimate was, and you did exactly the same amount of time, and everything was great. But this is what happens when you overestimate, which is that the penalty for effort increases linearly as you overestimate, right? So a linear penalty due to Parkinson's law. Unfortunately, there is an exponential penalty when you underestimate because there's a whole bunch of errors that crop up, there's a whole bunch of defects, and you start getting into high risk practices, and things just keep getting out of hand very, very quickly, right? So the graph is actually much worse on the underestimation side here than it is towards the overestimation side. Okay. Okay. The cone of uncertainty is a slightly scary sounding thing. What is the cone of uncertainty? This is the cone of uncertainty. Look at this scary looking chart for a bit. No, don't bother looking at it. I'll come back to it. What the cone of uncertainty says is that as the project progresses, estimates become more accurate. Obviously, that is that is quite obvious, is it not? Obviously, as the project progresses, estimates will become more accurate. Right? Let me explain this chart now. So, what this chart is showing is that this is actually time. So time is actually flowing here. And what this chart is showing is that as time flows here, the estimates actually become narrower and narrower as this path is followed, right? Which means that here at the beginning, when the project is at an initial concept stage, it's actually here in the, let me see this, at the initial concept stage, there is a huge amount of variability because no one really knows what they're doing. But by the time you finish requirements, the variability has already reduced because now you know more things about the project. You know what you have to do. You understand the requirements. You understand the potential dependencies in the system across teams, etc. Right? The same thing, when detailed design is completed, the variability is even lesser, right? Because you've already specced out things, models have been created, controllers have been designed, test suites are running, you probably have a CI server by that time, obviously, right? It's become even narrower. And eventually, by the time the software actually gets completed, everything converges here, right? There are two parts to this chart because everything below zero, this is actually what happens when you overestimate. And this part here is what happens when you underestimate. Okay. So the variability in the estimate. The reason this is important is because it's actually very easily possible to do worse than the cone of uncertainty, but it's not possible to do better because the cone does not narrow itself. So this narrowing bit here, you see this bit here where the cone is getting narrowed, this is not going to happen automatically. The only way this is going to happen is if these things happen here. So if we ask these questions, if during the initial concept, we ask the right questions to get to a product definition, right? And then you ask the right questions to get to requirements, and then you push for the UI design to be completed, you push for the detailed design to be completed. If you ask the right questions and if you do the right set of activities, the cone will get narrowed automatically. But if you don't do that, the cone actually does not get narrowed at all. What happens when the cone doesn't get narrowed at all? This is what it looks like. It looks like this, which is this was the best case cone. Unfortunately, for most software projects, this is what the cone looks like, which is that for most of the project, the variability actually remains really high. And it's only towards the very end right here is that the variability collapses and suddenly you realize, okay, I now know that this project is going to finish in 2 days. But before that, for many months preceding that, as the project is happening, the variability is actually really poor, right? So how do you get past this? One very, very easy way to do that is to stop doing first number in your head estimates because it sets the wrong expectation, right? What do I mean by that? Think of the last time when you were asked to do an estimate. Uh, and remember, try and like kind of close your eyes and remember that situation in your head. Your manager or somebody in your team, someone from leadership came up to you and they said that, hey, we're thinking of changing this feature or adding this feature to XYZ. How long do you think it will take us to do this, right? And in that moment, in that 1 second that you took to come up with the estimate, you did a whole bunch of random calculations in your head, and then you said some answer. Right? You said 2 weeks, or you said 5 days, or you said 3 months, etc. Right? What happened as a result of that is that you set an expectation in the other person's head. Because what the other person is doing at that point, unfortunately, the only thing that they have to rely on is your estimate. And once you set an estimate, they are going to take that number seriously and they're going to assume that that is close enough to the real number. And to understand how bad this is, I am going to take a 1 minute break. Okay. And I want you to think about the last time that you estimated something, whether it was a task or maybe a story or maybe it was a bug fix. Think about it in your head. Think about what happened after you gave the estimate. Think about how long you took to actually come up with that estimate. Okay, I'm still here. I'm assuming that people are thinking about this. And the reason I am doing this is because even a 15-minute estimate is exponentially better than an instant one. Okay. And why is that? To give you an example, I have now been doing this talk for about 16 minutes or so, I think, by my clock, right? And I've covered a lot of different ground and I've mentioned a bunch of different things. So even if you had taken this much amount of time to come up with an estimate, and instead of saying something which is the first number that comes to your head, that is going to be exponentially better in every situation. So take those 15 minutes and come up with a better estimate. Now, what do you do in those 15 minutes? I'll come to that. But some of those answers are already evident because later, once our estimates have failed, we realized what were the things that went wrong, right? And one big thing that goes wrong is that engineers don't include all the things that have to be done to produce software, right? Some requirements are stated. That's correct. Because there are some requirements that are going to be part of your user stories. There are some requirements that are going to be bug fixes. There are some requirements that are going to be in PRDs and stuff like that. So those are stated requirements, but there are other requirements that are implied, and those implied requirements also add to an estimate. For example, deployment setup, right? Deploying software takes effort. Setting up a deployment pipeline takes effort. You have to maintain a bunch of build scripts. That takes effort. You have to review the code that is being written. If you have a bunch of people in your team, everyone does a bunch of different code reviews, that those things take time, right? Writing documentation takes time. You need documentation because when you're going to onboard new team members, those new team members are going to read that documentation. If you don't write that documentation, when you do have new team members joining the team, you are going to have to stop the work that you're doing and then onboard those new team members, right? And that is going to stretch timelines again. Creating test data takes time. Upgrading dependencies takes time, right? So including everything when you're coming up with an estimate is really important because the complexity of what you're going to do is not just the 5 lines of code that you're writing. As engineers, it is a responsibility to get out of the whatever ID or whatever editor you're using to write your code and stop thinking of it in terms of code and start looking at it in terms of value that is being provided by the software that you're building. And there's a lot of things there. Cool. So what are some factors that influence estimates, right? Of course, a bunch of different things uh, contribute to how hard or how easy it is to do an estimate. But thankfully, a lot of people have done a lot of work. They have spent decades, in fact. So Steve McConnell's book, Software Estimation, actually has tons and tons of research papers and other books and academic references in the book about teams and companies that have spent millions and millions of dollars collecting data to figure out what is it that makes estimates hard and what is it that makes estimates easy. Like what are those factors? And let's talk about some of those factors. And schedule. As size increases, effort goes up exponentially. It doesn't matter because if the code base that you're building is going to be, say, 10,000 lines of code, right? And there's a different code base that you're building that's going to be 100,000 lines of code. Now, there is a 10 times, right, a 10x difference between both the code bases in terms of the lines of code. But the complexity difference is not going to be 10x, it's going to be 100x instead. Because there is just so much more that can potentially go wrong. And there are just so many different parts of the system that are interacting with each other. And it makes everything way harder. Right? And there are a lot of different estimation models and frameworks that are really boring, by the way. If you want to go this up, I'll mention some of those in the talk later. But there are other things that they came up with that influence an estimate. But everybody agrees that size of the software is the biggest difference. It is the biggest marker. It is the biggest reason which changes the estimate. Here are some others that actually make a big difference. Programmer capability makes a big difference, obviously. If you have a team of 5 engineers that are extremely, extremely good versus a team of 10 engineers that are fresh out of college, there is going to be a big difference in the estimate. Time constraints make a big difference to estimates. If you are under a time pressure, then it becomes harder to estimate. If you're not under time pressure, it is easier. Team continuity is a huge factor. If the same set of engineers ends up working on the piece of software throughout the lifetime of the software, estimates become better and better and better. You can actually rely on the data, historical data from the same project, and it makes a big difference because you now know how the team performs. Required reliability makes a big difference to estimate. Is that? Think about it yourself, right? Let's say you're building a to-do list application. Right? That doesn't really require a lot of reliability. But let's say that we are building software that is in the medical domain, right? Which doctors are supposed to use. Now that requires a very different kind of reliability that consumer software does. And that increased reliability forces engineers to make many decisions which you normally would not take, right? And that increases estimates as well. So 5 things that make a huge difference to estimates, and all of them, this thing comes from what is called the COCOMO 2 software estimation model. It's a very strange looking, say strange sounding name. Please go look it up later. It's very bunch of very scary looking charts. Um, you can in fact buy estimation software, which is built on top of COCOMO 2, so that you can estimate using a software how long it will take you to build some other piece of software. Anyway, important point. Now we've gone through what an estimate is, we've gone through what a target is, we've gone through how poor estimates unfortunately impact our lives, and we have gone through what actually impacts those estimates. Now, how do we improve these estimates? Now, I'm really hoping at this point, for this section of the talk, I hope you use story points of some type when you're building software. If you're not, I would recommend studying what story points are. I would recommend that you go read up about them, because this section is going to be a little more complicated to understand. But bear with me. Okay. So story points are a mark of complexity, and they don't necessarily represent time. Why do I say necessarily in brackets? Because in some fashion, they might represent time. From a team's perspective, they might represent time, but largely story points, the reason why so many teams use story points is because there is a lot of complexity. Okay. Now let's take an example. Let's take an example of a team which uses 1 or 2 or 3 points. That's the scale that they're using of story points for a certain project. Right? Now, it is possible that a junior engineer takes about 5 days to finish a 3-point task. Okay. Okay. A junior engineer takes about 5 days to finish a 3-point task. It's possible that a senior engineer will take 2 days to finish the same 3-point task. Because obviously senior engineer will work faster, it'll be easier for them to make many decisions, they will understand the code base better, they are more familiar with the language, the framework. I'm sure you're aware of those things, right? So the time taken is different, but the complexity of the task is usually similar. Now, this might be a little hard to understand, so bear with me as I give you another example, right? What are some examples of tasks that are not complex necessarily? Right? Create a lint step on the CI server. Now, this doesn't sound complex because it sounds like the CI server already exists. It seems like I just have to add one step to an existing server. Seems like the pipeline is set up, so it doesn't sound very complex. Add patient has already visited, option to an overdue list. Again, it seems like this list already exists. It already has a bunch of options, and we just have to add another option. So the flows and the controllers and stuff are already, it seems like they're already set up. So this doesn't sound very complex, right? But what is complex? Allow blood pressure measurements to be deleted. Now, this sounds complex because deleting some data requires a bunch of different things. How will the deleted data behave? Should it be actually deleted, or should it be fake deleted and hidden from the UI? How does the change propagate? Okay, this is a bunch of things, This sounds like there could be a lot of things in this thing, right? And I'll come to that later. But before I go to that, I want to talk about the law of large numbers. Right? The law of large numbers is that if you create one big estimate, your errors will either be completely on the high side or on the low side. But if you create multiple small estimates, some will be on the high side and some will be on the low side. Okay? Which means that the errors will cancel each other out to some extent. Let's repeat that. So if you create one big estimate, your errors will either be completely on the high side or completely on the low side. But if you create multiple small estimates, some will be on the high side, some on the low side. So errors cancel each other out to some extent. What does this mean? This means that when you see a big task or a big story or a big feature, don't estimate the feature at all. Break that feature down into different tasks and different stories, and then see what happens. Okay. Now let's look at this complex thing. Allow blood pressure measurements to be deleted. The example, this story, this feature request actually comes from an open source project that me and my team works on. And what I did was I looked at some of our stories that were really complex. I looked at our project management board, and I tried to see why was it that these tasks were complex, right? And that's because if you look at this story, allow blood pressure measurements to be deleted, this was what the task list was for that. Right? Now, this has been broken down by an engineer. And you can see there's a whole bunch of things here. There is some add remove button, there is some show confirmation dialog, there's some property that has to be updated, some other property, close the sheet, exclude something else, exclude somewhere else. Right? So clearly, it's very clear that once this engineer thought about deleting this object from the system, they realized it's not just about deleting a row from a database. There's a bunch of different things. There are some UI changes, there are some model changes, but there are also changes that affect other parts of the system. Let me bring up another example of what is complicated. Sync protocol runs across all facilities and display in the app. Ignore what it means. This is what the task list in our system was, right? So you can see a lot of different things, a lot of different moving parts, multiple different tasks, and the whole thing the code eventually touched many different packages, many different controllers, right? And you realize that it's only in retrospect that you realize that this was complicated, right? Which means that when you start off by looking at just a simple sentence, the only way you're going to come up with whether it is complex or easy is if you do this much. Is if you spend 15 minutes and then you try and understand, okay, what are the different things that I have to do to actually build these things, to actually build this feature out, and then try and understand, okay, it seems like there's a lot of different things. This is clearly not a simple thing. Okay, so some tricks. Trick number one, which I already mentioned, do a detailed task breakdown and spend some time. It is important for you to spend time. If you're going to spend a couple of days to build a feature or to fix a bug, I'm sure you can spend 5 minutes or 15 minutes of silence, of thinking, to actually do a detailed breakdown and to actually go through the code and just try to understand what are all the things that you will do. Spend that 10-15 minutes. It will be a game changer. It will be the biggest improvement to your own personal estimates. Right? Think of the worst case while estimating. Again, something as engineers we do poorly, and something that I'm very guilty of doing as well. Is that when we think of an estimate, we think of only the best case. We assume that everything will go correctly. We assume that all of the changes will be very easy to make. We assume all of the documentation will be available, etc., etc. But that's a very poor way of thinking about it. It's more beneficial to actually think of the worst case while estimating, because that worst case thinking will push you to come up with different situations that you might have forgotten, or situations that you just might have missed while building something complicated. Okay. Compare different stories of similar complexity. Again, that is something that's very useful as a trick, and it is so revealing if you look at a project management tool, right? And you go through the history of the project and you pick out multiple different 2-point stories. All of those 2-point or all of those 3-point stories should be of similar complexity, right? And that is a easy way to figure out that, okay, is my team or am I doing estimates accurately? Because if one-point story and another 1-point story and another 1-point story feel completely different levels of complexity, you know that you're doing a poor job of this and that you can improve. There is scope for improvement. So bringing up that data from measuring that data and looking at historical data of your own work is very useful. And comparing different stories is very useful. Use a project management tool that understands velocity. Again, this is a reference to all of those teams that use Google Sheets and Microsoft Excel to actually run their software projects. And that doesn't help because it's really hard to maintain an Excel sheet. But if you use something even as simple as Pivotal Tracker, Linear, it doesn't have to be as complicated as Jira. That's what I'm telling you. Even if you don't do something as complicated as Jira, many different project management tools are actually very far simpler, and they help you understand the velocity of a team. This is important because you need to understand that different teams have different velocities. But it's possible which means that it's possible that your team does 9 points of work in a week, but the backend team might do 12 points of work a week. But the front end team might actually do 20 points of work a week. And that is important. That historical data that a project management tool can give you, this velocity is important because it helps you when you start doing better estimates, when you start breaking down tasks, when you start using story points effectively, you will have a sense of how much time your team will take on an average. Obviously, this can go up and down, but on an average, you will have a better understanding of time that your team will take to finish a certain task, which has a certain amount of points. Engineers should break down tasks and estimate them themselves. Sorry, I missed themselves here. Um, this is a reference to many teams that I've seen where the project managers or the product managers are the ones that actually do the task breakdown. And that doesn't help at all because we as engineers, it should be our responsibility to break down those tasks because it's only us as engineers who can actually figure out what are those different moving parts of a system that will get touched when you actually build a certain feature. Sorry, look at past data for your team for similar type of work. Again, look at your own historical data. It's very useful. It's surprisingly useful if you maintain detailed enough log for a certain project. It is really useful to go back in time and see, okay, I have built a similar feature last year, and last year it took me 6 weeks to build this feature. Knowing that, it should kind of take you around 6 weeks this year as well. You might have improved as an engineer, that's possible, but that 6 weeks will not become 2 weeks. Right? So, and you can understand this for yourself personally only if you look at your own data. And it's highly possible that your team doesn't use a project management system, or maybe you're somebody who's working alone on a system. You should measure yourself. This is a suggestion that I've given to a lot of young engineers when they first start working, which is that what you can do to understand yourself better is maintain a private document, right? Every time you start working on a feature or a bug fix, write down, okay, I'm going to work on this feature. In front of it, write down the estimate that you think the amount of time that you think it will take, right? So say that I think it will take me about 2 to 3 days, and then write down 2 to 3 days. And then later, when you finish that, go and add in front of it, this is the actual amount of time that, and then be able to see that deviation yourself. So even if your team is not following these practices, and even if your company is not following these practices, just measuring yourself privately, having your own self be aware of how much deviation exists between your own estimate and your reality, that is also a very useful thing to have, and that will alone make you a better. So do it yourself. Okay, negotiations and agreements. An estimate is a conversation. An estimate is a negotiation. Why is that? Because an estimate has a probability that is attached to it. There is a certain degree of success or failure that can happen with an estimate. But also because engineers own the estimate, but management owns the target, right? And it's important to understand that the engineering team and the management team are on the same side are on the same team, right? And everyone's goal is the same, which is to ship the software to the users and benefit the organization, right? And the goal of this estimation exercise is not pinpoint accuracy. No one is interested in pinpoint accuracy of estimates. What people are actually interested in is they want to understand value in comparison to effort. That is what your leadership team or your manager is actually interested in understanding. Why is that? Why is it that they want to understand the value in comparison to effort, right? It's because management owns a certain target, and this target could be maybe you have an investor meeting. Maybe the target could be that some sales quarter has to be. Maybe the target is that a certain PR campaign is being run by the marketing team. You have to finish a piece of software by the time the campaign starts, right? Those other things that an organization must do, right? And every organization does that. Those things are usually not movable, right? And lots of different coordination happens between different teams. But it's important for engineers to understand that the estimate can match a target, and you can have a conversation in a way that all the stakeholders agree that this is the time that we have, this is what we can do, and let's try and match these two together. Right? And one very easy way to do this is to do t-shirt sizing, right? And I'll give you an example of this, right? Let's say that you have 4 features that you want to work on. There are 4 features. These 4 features, management says that it is important for feature A, feature B, feature C, and feature D to finish by the end of the month. They said that no, you have to finish this by the end of the month. And you, as engineers, already know that this have to finish by the end of the month doesn't mean anything, because if you cannot finish it, you cannot finish it, right? And therefore, as engineers, you say that no, this is not possible. I can't finish ABCD, all four of them by the end of the month, right? And at this point, suddenly negotiations break down, right? Conversation breaks down. People get pissed. Nobody wants to, continue the conversation. But a very healthy way of breaking out of that conversation is to do what I call a t-shirt sizing exercise. Right? And in a t-shirt sizing exercise, what you can do is that you make two columns. You make a column for value and make a column for effort. Now, what happens here is that let management figure out what the value of each feature is. So feature A is small value, feature B is medium value, C is small value, D is extra large value, right? This is useful. And then what engineers do is that they can come back with what the effort is, right? Medium effort, small effort, large effort, medium effort. Right? And now that the engineers and management are looking at this together, one thing is very clear. The first thing has small value but medium effort. That's not good. This thing has small value but large effort. So clearly A is already better than C, because A and C provide, management claims that they provide the same value, but the effort for doing A is better. The effort for A is smaller, right? But the other thing that's important is that this is medium value, more value than A, but the effort is actually lesser than, right? That's great, which means that B is now automatically more important than A, right? And so on and so forth. So this is a very useful and a very easy exercise to have a conversation between different stakeholders of an organization, um, and to try and understand, okay, what is it that we should actually do? Because once you've done this exercise, then it becomes easier to convince somebody that, hey, you know what, we should probably not do C, because C has the least amount of value and the most amount of effort. Let's cancel C. And at that point, then management understands that you, as engineers, are now separating people from the problem, and that's a great thing to do. Because otherwise, everyone, all the different stakeholders in an organization, seem to think that they're all looking out for their own neck. But by having a conversation, by having a dialogue around negotiation, it helps to prove your point that, listen, I'm willing to separate the people from the problem. Let's all focus on the goal, which is we have to deliver software. Right? So focus on the interests and not on the position. It doesn't matter if a project manager is saying something. It doesn't matter, but that matter if it's a junior engineer or a senior engineer or the CEO or the CTO. That doesn't matter. Let's focus on the interests. Let's focus on what is it that we're actually here to do than on the positions, right? So that we can come up with options that benefit everyone. Because that is what everyone's trying to do, right? At the end of the day, once you've done your estimation, you've done your negotiations, you've written the code has been shipped, etc. What everyone wants um, are options, and what everyone wants is a situation where everyone gets benefited. Because either everyone wins in the situation or everyone loses. Right? And why is that? It's important to understand this, because even if you, as engineers, present a certain estimate that everyone is really pissed about, and then you meet that estimate, it still did not help did not help the team, or did not help the situation, because that was not the timelines that they were looking at, right? So that estimate is not something that is set in stone, right? And it is helpful to have that conversation about that estimate with everyone else, so that everyone can win together. Otherwise, it just doesn't help everyone, right? That's all I have for today. Go forth and estimate. I hope you do this uh, better. Thank you so much for giving me time on a weekend. Wear a mask, stay at home, and wash your hands. Thank you. Okay. All right. I don't know if we have time for questions. Do we have time for questions?
Pratul, there are a couple of questions in the chat area. Probably like the one question like
Okay.
Manish asked was, what project management tool you guys use? That obvious.
Uh, um, I would prefer using what is called linear. I'll just post a link. This is one thing that I would technically prefer using. We don't always have a choice, because we're a consultancy and we work with other organizations, and sometimes they have their own thing. But if you had asked me to choose, I would choose between linear or Clubhouse, like both of them. a bit. They're both very simple. They're very beginner friendly, and that's very important for teams, especially when they're getting started. Thanks, Rajat. Okay. Yes, that's true. Brijesh is correct. If you have a S value feature with Excel efforts, obviously it doesn't make any sense. Okay, any other questions? What if a manager decides to estimations for their resources? Not sure, Prachi, what you mean, but I think if I understand this correctly, you mean the manager is the one actually doing the estimation instead of the engineers? But I think overall that's a bad idea, and you should definitely fight against it. And maybe go talk to your manager after this talk. Now that you've listened to this, and try and have a conversation with them. That if I mean it's pretty ridiculous. I have sometimes given a different example for sometimes leadership teams at client organizations where they say that their managers do estimates. And the example is this, right? Let's say that you're trying to build a house. And you have a lot of money, you decided to build a house for you and your family, and you go to a great architect, and the architect is like, you know what, that's great, you have this great idea. I think the house will take a year to build. Okay. Now, at that point, do you go and tell the architect that why does it take a year to build? Like, should you be able to build? This should be possible to do in 3 weeks, right? And nobody will ever say that. Right? You will never go to your architect and say that why don't you build this in 3 weeks instead? Because in your head, you know that the architect is the one who's going to actually design and build the whole thing. So you will trust their estimate much more than what you think in your head. And maybe it might help to give an analogy like this to your manager, that let the people who are actually doing the work do the estimates instead of you thinking of an estimate which isn't of any value at all. Okay. Other questions?
It looks like nothing.
Okay.
Thanks so much, Pratul, for coming.
Sure. Thankfully I didn't have to come all the way to Bombay, but I would have quite enjoyed that, I think.
Yeah, this whole thing has opened up a lot of these barriers for us.
That's true. That's true. Okay, thanks, Manish. I am on Twitter. You can always just send me a tweet or something. Happy to continue the conversation. Okay. Thanks, everyone.
All right. Next up is Arun. Arun, are you ready?
Yeah. Can you hear me?
You can. Yeah.
Okay. Thanks, Pratul, for the talk. It was really nice. Learned a couple of things actually. I'll start by sharing my screen now. Please let me know if you're able to see. You guys are able to see my screen?
Yes, sir.
Okay, yeah. So we'll follow the same format. Like, please, if you have any questions during the talk, please let me know in the chat. We'll spend some time at the later part after the talk and discuss the questions. So so bit of introduction. This is Arun Kumar. So I'm currently located in Singapore. So I work for a company called Grab. So it is a ride-hailing company that you might have heard about, similar to Uber, Gojek, and we primarily serve the Southeast Asian market. So today I'm going to be talking about modularization strategy for better Gradle build time. So before we begin, I would like to talk a little bit about myself. So I currently work with Grab in the mobile platform team at Grab. So we have a couple of verticals in Grab. We have the consumer app team, the driver app team, the merchant app team. So I primarily work with the consumer app that the general population typically use. Within the team, it's been over slightly bit over a year since I've been working with Grab. So primarily work on build systems, fighting with Gradle a lot, try and reduce our build time by any means possible. So previously, I used to work in a company called Freshworks based out of Chennai, where I worked on a small scale app, B2B app. Then before that, Bytemark in Bangalore. Uh, then I had a couple of experience in publishing my own independent projects on Play Store. So before I picked up a full-time job, I used to be an indie dev. With that said, the agenda and the motivation for this talk is basically from one of the projects that we did at Grab in the recent years. So we saw that our Android project build time was increasing a lot. We did have a couple of guidelines set in place when we had one of rewrite sometime on 2017, which was before I joined. But we saw that the build was not scaling as much as like we want to. So we sit together and decided to form a strategy that we can use for refactoring out or improving our build times further, and then also serve as a guideline for future modules at Grab. With that said, the agenda for this talk is going to be, I'm going to be a little more primitive in this talk. By primitive, I mean I'll be starting from the basics on a typical build systems, try to point out the problems that we are solving along the way, and then talk about Gradle and some of the optimizations that that we recommend to our teams here. With that said, in order to set the expectations straight, I'm not going to be talking much about Gradle configuration on the or some magical flag that you can turn on to reduce your build, because I do believe a talk like that would content like that would deserve a separate talk on its own. There was one recently by Nilsson from Gradle. It was on DroidCon online recently. I'll make sure to link that in my presentation when I share it online. So with that said, let's begin. So let's not talk Android or anything at all. Let's consider a very simple build system. So what a build systems typically do is we have basically two things. We have inputs and we have outputs, right? A build system typically comes in the middle. It takes the input, does some work on it, and then finally produces the output. In context of Android, this is a couple of things, right? You have Kotlin source file, Java source files, resources, AIDL, native libraries, dependencies, and so many things that we have in our code base. We do the build and we finally get the output, right? Now, in a context of a very simple single step build, what do I mean by single step build? Is that assume I'm writing a shell script or something that magically assembles the APK out of all these things and then finally produces the output. While this works, what are the problems that we face here? Let's talk about that a bit more. So the first thing is we did not, like, this is a shell script that simply executes it, right? So there is no caching or any parallelization capabilities. We execute this bit of work all the time, regardless of any changes in the input or something. Now, the same build step, let's say that it takes around 5 minutes to complete. So, and every time I make some changes in the code, I have to spend 5 minutes waiting for it to complete. And that gives a poor developer experience, right? So as developers, we want this feedback loop. We want this immediate feedback loop where we can validate our changes on the fly and make decisions faster. So having a slow build time hampers that by a lot. So even one of the Flutter's main goals was to provide hot reload, something like what they have been doing in web. So that's pretty cool. So in a simple build system, these are the problems that we have, right? The single step build system. Now, let's try to optimize this in a very naive manner. What I'm proposing here is that why not do something called hashing? So what do you mean by hashing? So what I'm proposing is, can I have this one-on-one mapping between input and output? That means, let's take Java class for an example. If I execute Java C on it, I'm going to get a class file. And can I establish that unless I change the Java class, the Java by source file, like add a method, add a parameter or something, the class file is always going to be the same, right? With these assumptions, what if we say a single Java file, unless modified, will always produce the same class file? So if the class Java file did not change at all, we don't need to do this work, right? So there is no change in the input. So what we can say is that we can skip the build process altogether, right? So we'll probably save a lot of time. So we do the build once, we don't change anything, and then we build again, and the build finishes like magically very fast, probably a couple of milliseconds. So everybody's happy, right? So this sort of a single step build with hashing possibly solves our problem, but does it actually solve? In terms of practicality, does not solve any problem that we are having right now. Why? Because as developers, very rarely we do builds without changes, right? So maybe I don't know about you guys. I do, like when I'm debugging something, I simply rerun without making any changes, hoping it works the second time. So that is different picture. But the point here is that we did not solve the core problem that the single build step takes 5 minutes to complete. Now, let's think about ways that we can improve this further, which is how to optimize this. Let's try to bring this 5 minutes down to like possibly a couple of minutes hypothetically. So what can we do? We have the same step, which is there are inputs and outputs. I forgot to mention, you are seeing this directed line connecting these two. So what I mean here is that there is a dependency, right? So the output depends upon a build action, and the build action depends upon an input. And I also established we'll be doing some sort of hashing to create that, okay, we have this one-on-one mapping. So if the input did not change, we'll not be doing any work at all. Now, what if we do something like this? Why not break this build step into 2 lanes? I would not be comfortable calling it stages at this point. This I would rather prefer it call it lanes. What I mean here is that why not split the inputs into multiple split the inputs. For example, this is an hypothetical example where we can have this: the first lane process the Java classes alone, the second lane process the resources, etc. So if we make a change in the Kotlin or Java files, somehow we can avoid doing rest of the work, like processing resources or something like that. So we are slowly solving the problems, right? So even though it takes 5 minutes for the first build, the second time when I'm making some changes, if the change is on the one side of the lane, the other lane does not need to execute at all. So we'll possibly look at saving some cost, right? So this is called fine-grained inputs. This is very important for caching, which I'll be talking about in the later part of the presentation. So as I mentioned earlier, we'll be re-executing the build lane only when changed inputs are directed for that lane alone. If it is not there, we will do that. So we are slowly getting there. We started with a very primitive single step build system, and we're slowly ramping up and trying to find ways to optimize it. But can we still do better? Uh, of course, I do believe we can. To find out why, let's take this single build lane for example. Um, by single step, like even though we broke this build into multiple lanes, we have this single build action which might be doing a couple of things, right? Within context of Android, there are so many things going on, and more recently, annotation processors started getting popular. We do a lot of manual mundane work. Instead of doing manual mundane work, we prefer to generate the code instead. Then we have Kotlin C, we have D8, then we have packaging, signing, all these things. So in context of Android build lane, a single build lane might be doing so many tasks like this. So my shell script that I talked about earlier would be doing something like this, right? But if you think about in terms of each individual unit of work here, they uh, depend on something else. Take packaging, for example. So packaging action is something that happens typically during the last stage of the build, where the APK gets built, right? So in order to build the APK, you need compiled dex files, processed resources, any metadata, native libraries, and something like that. So I can say that this packaging depends upon AAPT, D8, native code compilation, etc. Similarly, I have this signer action here. So it basically signs the APK for security purposes so that malicious actor cannot change it. So the point here is that signer needs the packaging actions output to work, right? So that means there is a dependency there. So like this, there are some. This is not fully exhaustive look at Android actions, but this is just for demonstration that I want to say that the dependency and there are interconnected actions in part of a single build lane. So the same diagram here, but what I did instead was I split this build lane into different stages. So for example, here it could be the packaging and signing that I talked about. The first could be the final build block here could be the signer, and before that it could be packaging. And since I have an arrow pointing towards, there is a dependency chain involved here. But in context of real Android build time, in Android build, we actually have something like this. So most of you probably recognize this. So I'll be explaining on this a bit more. So basically, we have a directed acyclic graph here, right? So why this becomes important here is because there we can notice several things here. First, take a single circle here. A single circle depends upon an input and it passes the output to other circles here, right? So the circles here are node, and each node represents the build action. So the first thing is fine grade inputs. So we learned in the previous slides that when you reduce the number of inputs to a build action, you have this higher chance of not doing anything when you're when you want to build your app, right? So for example, this highlighted node here could be some the .so files which you do not touch at all. And when you build the app, you change something else, and this just because of this fine-grained inputs, it does not do anything. It just gives you the cached output here. Second of all, the most important point of this diagram here, which is independence. What I mean here is that we started with a single step, right? Where every the 5 minute skills imaginary shell script that I was talking about was taking had only the source file as the inputs and the outputs. It executes all the time. But here, when we have nodes like this, we have the interconnected dependencies. we can actually find a couple of nodes which are not related to each other, right? Take this and this, for example. They are not dependent on each other. Say they depend on a particular input from the source file. So this could be the SO file that I talked about. The other one could be a capped task, which is Kotlin annotation processor. So what, since they are independent, we can possibly execute them in parallel, right? So by executing them in parallel, we obviously save a lot of time. So the same applies recursively for the entire graph. Um, so as I mentioned earlier, these are acyclic graphs. So you would have seen this firsthand. It is used everywhere. Almost all build systems talk about this. It has plenty of applications. Even Dagger, the Dagger name comes from DAG. You cannot have cycles here. Why you cannot have a cycle here? It is literally not possible, right? You cannot cause a cycle because that is illegal. Now, turns out whatever I've described so far is actually Gradle, right? So in the previous slide, I talked about this nodes and the interconnected dependencies and fine-grained inputs and stuff like that. But actually, this is what I was talking about Gradle. Gradle is structured like this. So you have a set of input files, you have a set of output files. Gradle comes in middle. It establishes something called task. Each task has an input and output. The input can be your raw source files, or it can be an intermediate output of a previous task. So what I have been saying, actions so far in this explanation, what I was talking about is actually Gradle tasks. Now, with this information, I'm going to make a case for modularization here. So I want to say that people should be modularizing their monolith projects more, and the reason being parallel execution. So this is the one of the case that I want to make as part of the strategy, which is Gradle supports parallel execution for a while now. I don't remember the exact Gradle version, but it is in incubating mode right now. But I can tell you that we cannot imagine our Gradle builds without this flag. It would be unbearable. So the same concepts apply, right? So if for the same code base, let's say we have like 100 input files, we have a DAG possibly containing 10 nodes. That means among those 10 nodes, the independent nodes can be executed in parallel. So, but what are you doing by modularization? By creating a new module, you're actually increasing the number of nodes in your build graph, right? So what happens there? So when you increase the number of nodes in your build graph, by the logic of DAG, as long as the nodes do not depend on each other, they can be run in parallel, right? This is the first case. The second one is I want to talk a little bit more about Moore's law here. So one of the opinions that I've seen online is that why spend a lot of time on modularization? Just buy a powerful machine, just buy a top of the line Mac, so all your build problems will go away. So I want to challenge that fact with Moore's law. Why? Because uh, Moore's law says that the number of transistors in a CPU will be doubling every years. That means our CPUs will become more faster, but that actually turned out to be false. We started our CPU growth stalled a couple of years back, where we were not able to push out fast CPUs, but we were able to push out multi-core CPUs, right? So we were able to offset the stall in frequency by adding more CPUs, right? What this allows us to do is that when we have multi-core CPUs, we'll be able to execute our DAG in parallel. For example, Gradle determines the number of threads for parallelization based on the number of CPUs. So if you're obviously executing in a powerful multi-core machine, you'll experience faster build time. Whereas if you execute the same code base, if it is monolith on a single powerful CPU, you would only reduce the execution time of a single task. The entire build time would be closely similar. Let's find out why at the later stage of this talk. Um, then this is cache ratio is important. At Grab, we use Gradle remote cache, which gets populated from our CI. So we have this ingrown in-house Redis cluster where we populate all the artifacts from CI there, and all the local builds share these results from there, from this remote cache. So this is one of the other factors for improving our build time. So all local, when you're pulling a latest master, and if it is already built on CI, your local will be miles better, because CI, you're able to share your results with CI. Now this is very important for modularization, because when you have lot of independent nodes, your inputs are fine-grained, and Gradle uses these inputs to determine whether it can use a cached result, right? So when you have more modules, naturally the number of files to check for getting the result from cache reduces. That means you have more chance of hitting the cache when you have more modules. So in summary, parallelization and caching and the way our CPU growth are going are the major points that I want to make in term as a case for modularization. Now, let's get to the specifics of how parallel builds work, right? So, as I mentioned, Gradle, even though it forms a DAG, it only considers different projects as independent tasks. So, when you have a single monolith module, your single monolith module might have as a DAG, like different nodes for packaging, signing, stuff like that, but they may or may not be executed in parallel. However, if you break that monolith into different modules across your code base, all those modules will get executed in parallel as long as they're independent. However, as a side effect, you would see that your memory usage goes up, because parallelism is a really a hard topic even today. You could see still people trying to find out ways to avoid this. You have Kotlin coroutines and stuff like that. So memory goes up because more code is being executed at the being processed at the same time. So because of these reasons, Gradle considers parallel executions to be incubating, but I'm confident that we can enable it locally and evaluate as needed. Then we have this thing. I already mentioned a couple of criteria for parallelism, independent tasks and stuff like that. With that said, to expand upon, we have this point where I mentioned that parallelism depends upon your project structure. So we are closing in on the crux of this talk, which is how your project structure determines parallelism here. So when your build is parallelized well, you will end up saving a lot of time, because you utilize your cores on your machine well, and um, at any point in time, you are able to utilize all the threads on your machine. But is there any scenario where you are not able to utilize this all the threads on your machine? Let's find out. So let's take this simple build scan. So for those who are not aware, build scan is a first-party Gradle plugin which is used to analyze the performance of your build. It has detailed statistics. It has timeline view. It has inputs and outputs. It has reasons on why some tasks executed. It can show you which plugins contributed to your build. So again, I'm not going to delve much on that front, but I'll be talking a little bit on the structure here. So I have A, B, C, and D and E. If you can see here, it takes around 8 seconds to execute this. And presumably it executes on two threads here. And as you can see, I'm not being a lot of parallel here. More than 50% of the time is spent on a single thread, because here A is slow and E is slow, so they are executed on a single thread. We are not utilizing the parallelism here, right? So through little tweaking, we determine that um, E is actually not dependent on D or B or anything. So E can be uh, we don't need the dependency. We don't need any dependency on the other projects. So when we make that change, what happens is that A and B, so A and E, they start executing in parallel, and similarly, the same way before, B and C are executing in parallel, and finally D. Now, what happens here? We reduced our build from 8 seconds to 5 seconds here, which is a considerable win. Now imagine somehow you're able to apply these sort of optimizations to your Gradle build such that your build becomes more parallelized, uh, and thereby reducing the execution time. So that will be the crux of this talk today. I'll later expand upon this and share the formal modularization strategy that we developed at Grab, accounting for this fact about increasing the parallelization of your build. So the thing that we are going to be talking about is something called critical path optimizations. So if you're like me, I Googled it for the first time. I got shown a couple of project management slides about how to manage your project effectively and stuff like that. I was quite surprised in that regard. But critical path is heavily related to a graph, right? Particularly directed acyclic graph. So let's try to define it, and then similarly to before, I'll be illustrating what a critical path is with help of graph diagrams. So I'll be delving a little bit on graph theory here. So hope you find it interesting. So a critical path in a directed acyclic graph means the longest chain of actions that must execute sequentially, right? So far I've been pushing for, okay, break down your monoliths, add more nodes, be independent. But turns out we don't always have this privilege of breaking down modules left and right, because this is built by Android Gradle plugin, right? We have a lot of plugins that we add. So all the tasks are configured by those plugins, and definitely there must be a chain, right? For example, as I said this earlier, packaging and signing cannot happen until the APK is built. So it must always execute sequentially. So what they're saying is that, so the longest chain of actions, such actions that must execute sequentially, is called a critical path. And since these actions depend on the previous actions output, they can never be parallelized, right? So same example, packaging, signing will never happen without packaging being done. So even when we throw multiple cores at it, that is not gonna be parallel. With that said, the critical path execution time is the lower limit of your build. I should emphasize that it is a lower limit of your clean build. So we started with a single step shell script where it was building for 5 minutes and stuff like that, right? So the critical path of that single step would be 5 minutes. You cannot go less than 5 minutes until you do something, because it was sequential all the time. So similarly, in a DAG, there exists a path, and your build cannot be any faster than this path. That is the critical path execution time. And if you manage to reduce this critical path execution time, your build naturally is gonna get faster. Let's find out why in the later part of the slides. Before that, I would like to emphasize that, so you have a directed acyclic graph. Right now I have an i7 machine. Let's, for hypothetically, throw more core at the build by building it on a powerful AWS instance or something. But these tasks, the critical path task, they will always execute in parallel, right? They're not going to be parallelized. You might definitely see build improvements, but it's not going to be factor of huge if your critical path is worst, right? So same example, you have inputs, outputs, DAG that processes inputs, and finally you get the output out of here. Now, I mentioned the critical path is something that longest, right? So in order to quantify something, we need weights assigned to each node. So in this regard, the weights to each node becomes the execution time of the task. For example, if I do assemble debug, it is gonna do compile Kotlin debug, uh, capt generate package signing, AAPT task will process all the resources. Each task will have a time associated with it, and if you use that time as a weight for these nodes, you can calculate the longest chain of, this is opposite of shortest path algorithm, which is this is longest path, basically accounting for sequential builds. So here I purposely gave large numbers to demonstration purposes, 7, 4, and 5. It's gonna be hard. Now here, these 1, 7, 4, 5, and 3 always gonna execute in sequentially. Now let's find out how this negatively influences the build. Let's take another fast path here. So obviously this is going to be a fast path. It's only 5 points, whereas the other one has considerably high amount. So I'm gonna name it A and B, right? So B is definitely gonna finish faster because the time taken for it to execute is very less. However, A is gonna do this. Now, when such a situation happens, note the highlighted area where in order for the node 3 to start, right, both 5 and 1 has to be finished, right? So what happens here is that your build is actually waiting for the another path, another lane to complete, right? So even though the B finishes in let's call it seconds, it waits without proceeding until the critical path finishes executing, and then 3 begins and it outputs. So this is very easy to relate, right? For example, you have we don't have any resources in the module at all. You don't have data binding. You just have a couple of Kotlin files. Obviously, the resource processing is going to finish early, and naturally, Kotlin processing might take time. But when it comes to packaging, you cannot do the packaging without resources, right? So you need both resources and the Kotlin or Java dex files to do the packaging. So you're basically blocked. So the proposition that I want to make here is that somehow, if this critical path is reduced, I would confidently say that your entire build is going to get better because the build is going to become more parallelized. So let's see how. Here we have this node called 7 here, which is like the biggest task in this project. Now, what if we break down this task into multiple tasks, right? What happens is that you end up creating more nodes. So when there are more nodes, you're creating more independence, right? So this is the natural, like when there are let's say 7 is a module, like a very big module. You determine it is in a critical path. You break that module into multiple modules. Then what happens? This 7 possibly becomes 3 and 4, but then the critical path ended up reducing a little, right? So that is the proposition that I want to make here. So when you want to modularize your project, modularize based on critical path. prioritize modularizing modules which are participating in the critical path. Why? When you do such a thing, they are usually um, big tasks, so they get reduced. So the build becomes more parallelized. And this has another side effect. When you break down the nodes into multiple nodes, your chances of parallelism improves. At the same time, your chances of caching improves because the inputs are becoming fine-grained more and more and more, right? So that is the second thing, caching. With that said, let's recap a bit. I agree it was a lot of theory, but I want to give a clear picture on how critical path influences your build time. So when you're actually doing the refactor, you have these indicators on like what might be actually blocking your build. So far, I've made a case that modularization helps in build time, and it does so by parallelizing your build. And when your build is parallelized heavily, multi-core execution time is going to be a lot better, and you will definitely see improvements there. And then, in order to influence the build improve the parallel building, we defined a term called critical path, and established that if you have a worst critical path, like the 5-minute shell script that I was talking about, your build is not going to get any faster than the critical path time. So this is what we have covered so far. This is a lot of theory. Now let's talk about practical aspects of optimizing this critical path, right? So the same example, I broke down the 7, right? I broke this 7 into 3 and 4 in the slide earlier. Now what happens? The critical path keeps on changing. So it's not like a single effort where, okay, I come to work today, I look at the critical path, I get the task that, okay, that module is in the critical path, I do some refactors, and I'm done for the day. But no, it is an ongoing process where we understand the build structure more, and then we look at the parallel metrics and see, okay, we still need to do it more. So teams can do it at their own phase. At Grab, we requested a specific tech families. So we have different teams to look at. We identified the critical path times and then ask them to refactor out modules, and that's how we approach this problem. Now, since the critical path is going to be changing a lot, you'll also be able to predict which modules are gonna be the next candidates for critical path. So for example, if I break 7 into 6 and 1, I know that 6 is going to be in the critical path next, probably, right? However, if I break it into 3 and 4, and I have another node which was 6, then the new critical path is going to be the other one. So when prioritizing the modules for modularization, you need to look at both the current critical path and be able to predict, okay, these nodes are going to might be candidates for critical path later on, so it is worth looking into it. So second thing, so far I've talked exclusively about clean builds. I did not talk about incremental builds. So because when you do an incremental build in the same DAG, all the if the task was up to date, like it did not do any, because the input did not change, it is always going to be 0, right? So your critical path is influenced by incremental build. So all the benchmark builds that you do for critical path calculation should be a clean build without any caching. So you basically force all the tasks to execute so that you get a clearer picture on how much amount of time each task takes, right? So let me show you a couple of internal tooling that we built at Grab. Unfortunately, it is not open source. I would prefer it was open source for this talk, but we are still looking down the line and prioritizing this effort to decouple couple of grab stuff and then look at open sourcing this. So what we do have is a scheduled job which populates something called the critical path dashboard. So on the right side you see this stacked bar graph, so where which is the execution time of the entire critical path, and each color there is the module. So you know that this module takes this much time to build, and with that, in this way we are able to track the changes as well, both historical and the current critical path execution time. Secondly, I mentioned that we cannot blindly ask in this say that okay, module C is in the critical path, you do it, and then you realize that somebody else made some other team, they reduced their module size, so your module became in the critical path again. So in order to avoid these things, we built a visualization. So what this visualization does is that it visualizes the entire project dependency graph, and it highlights the critical path on that build. Here on the right side, you can see app module E, A, B, C, D are in the critical path. At the same time, I see another module F, and you can notice that all these nodes are colored differently because why? Because their nodes are colored based on their build time. So here module C takes 122 seconds to build, whereas module F takes 77 to build. Sorry, 7 seconds to build. Now, obviously, module C is the best candidate for breaking down. At the same time, I see module D and F, which are next likely candidates to be in the critical path. So the prioritization would be first break down C and then look into breaking down D and F as well. This is the summary so far. Then the second bit is depending upon bridge API modules instead of implementation. The highlighted bit. I would like to talk a bit more on this. This is second part of our modularization strategy. Now, at Grab, we have different teams. We have transport team, we have food team, we have payments team, and a lot of teams there. And we have at instances there might be dependency between teams, right? You want to be using some of the modules they have built, and you want to share some functionality, which happens very often in a super app. They suddenly we want some banner to show or something like that. So you get this requirement that you need to use some classes. So what you naturally we see that those classes are present in module B, and in name of not repeating ourselves, we added this dependency on this module B and finished the feature and call it a day. Now, what we did not realize is that this module B is owned by a different team, and they have this control over it, right? So what happens if this module B grows considerably over the next year, right? What happens? So you are only dependent on a few classes there, and since this module B is growing considerably, you are basically blocked by your build time gets worsened because these classes needs to be compiled before. Even though this is only few classes, you are actually waiting for the entire module B to complete. So this is bad in terms of parallelization, right? This is similar to what we have mentioned before, like we need to keep our dependencies lean as possible. So in order to tackle this problem, at Grab, we have a convention called bridge modules. So what we propose is that whenever we want to change something, change or use something from a different module, you should not import it directly. Rather, you should import something called the bridge module. As you can see here, module B API, it just few interfaces, right? So you explicitly define what you want to be shared and what you don't want to be shared. What you don't want to be sharing is your implementation. What you can share, however, is the interfaces, right? So we make sure that module A depends upon couple of interfaces and does not depend upon the implementation. The implementation can grow by a lot, but since you depend on interfaces, you are not blocked. Your module is going to compile faster because all you care about are those interfaces that you implemented. So how do we connect this module B with this implementation? Obviously, we use Dagger, and Dagger generates code that connects this module B and implementation. And it happens at compile time behind the scenes. We don't need to be worried about this. As a side effect of this, there are a couple of advantages Gradle has implemented. One of the thing is called compile avoidance, meaning let's take a function, okay, function called main. It takes an argument and you add two numbers and do stuff like that. Now let's say module B has this function called main, and the implementation is written in module B IMPL. Now when I'm building, right, like I'm making some changes on the IMPL module, like instead of addition, I'm going to do some division or something like that. But the change that I made is purely logical. It is not API change, right? So the change only matters at runtime, whereas the rest of the code uh, stays the same. So in this regard, Gradle can actually stop, not compile the module at all. So it avoids. This works great for Java, but it has poor support in Kotlin. So there is a pending tracking issue there. I think we might see in future Kotlin releases, but I do wish it worked today. So with that said, I've talked about a lot of things. I've shown about dashboards, but what tooling that do we have today that might be helpful for you to have this feedback loop of looking at your critical path, doing some changes, ensuring that your build is parallelized, and what tools that we have. So one is Gradle build scan. You can use Gradle build scan, look at the timeline, and look at this. So one thing that was very surprising when we started this project was that Gradle makes very little mention of critical path in their official documentation, whereas other build system which works in the similar manner, processing a directed acyclic graph in a parallelized manner, they actually print out the critical path. For example, this is an example from a Bazel build. You can see critical path execution time was 41.81 seconds. That means that the build is not going to be any more faster than the critical path, and the elapsed time is 48, which is the total time taken. So Sung or Buck build system also has the ability to calculate critical path. But what about Gradle, right? What tools do we have? So we have one of these tools, official tools that got released recently, which is called Build Analyzer. Let's see the definition of Build Analyzer. For a given build, the Build Analyzer highlights the set of sequentially executed tasks that determine the duration of the current build. Addressing inefficiencies in this highlighted task is the best starting point. So this is a different way of saying that is your critical path, right? So sequentially executed tasks that took the long time, that is exactly the definition of critical path. So even though the Android Studio build analyzer does not reference it, that is what it means. So you get this, after you finish the build, you get something called a build analyzer window where you can see the entire task list. And you can see by each task and how much time do they take. For example, here you can see that merge release resources takes most of the time, and then we have also a couple of other things like Dex builder. And in this example, Santa Tracker is an official Google project. It is a multi-module project, and you can see module tasks from different modules being printed here. So your best bet is to start breaking down things. Breaking down modules presenting participating in this critical part. So we have capped debug Kotlin, which could be broken down. So with that said, how to actually do this? There are a couple of gotchas. As I mentioned earlier, critical path is influenced by whether your build is incremental or clean, right? We need to know the execution time of all tasks, and that can be only done when all the tasks are executed. So to do this, we can do add rerun tasks to your compiler argument and no build cache. So ensure builds are purely executing, and then we have then what you want to be doing is that look at your critical path from Android build analyzer, modularize, run it again and see if your build time is improving, and repeat it again, then you hopefully you will end up with reduced build time. Now, so far I've been pushing for modularization. I'm saying that prefer modules, don't prefer monoliths for in sake of productivity, stuff like that. But I would acknowledge a couple of concerns here. Gradle has this step called configuration. So before it executes all the tasks, it's gonna spend some time configuring this, configuring the project. So when you have more number of modules, you have more number of tasks to configure. That means your configuration time is going to go up. However, this is a willing trade-off that I want to make, because configuration time would be couple of, in the worst case be in minutes, in the best case be in seconds, whereas the build execution time will always be in minutes for a large projects, right? So I'm willing to make that sacrifice. There are a couple of improvements being planned. Kotlin 1.4 will implement something called lazy task configuration, where, for example, if you do assemble debug, only tasks required for assemble debug will be configured. The rest of the task will not be configured at all. So it'll possibly save some time. Then we have something called configuration caching, which is going to be part of AGP soon. I think it is in Canary right now, but I'm not sure when it is getting stable. Then there are this general, right, how to define responsibilities and scoping. So you'll have to invest a bit of time to define responsibilities of each module and stuff like that. So that is a downside. Now, this is the official things that I want to talk about: critical path optimization and how to improve parallelization of your build. So, but however, we're not in the where we want to be in regards to this. So we want to be looking at a different metric for critical path. Why? Because let's say we spent so much time, we optimized the critical path, we brought it, let's say, from 2 minutes to 1 minute or something like that, and then later on we make some code changes as part of development, and the critical path is going to increase. We need to prevent it, right? So in a very small project, it is very trivial to run it as part of your PR pipeline, and if your critical path, if you determine if it is increased, then you can break it. But in our case, it was not possible, because we were relying on caching and caching and up-to-date checks, right? So this makes it impractical to build it. So we only run it as part of a scheduled job. However, are there any other metrics that you can use? For example, LOC per module or something like that, which needs to be explored, which we prefer to do. Build Analyzer currently is heavily tied to Android Studio. I do wish if it was built as part of the Gradle plugin, and that works via command line, so that we can report it somewhere. I do have interest in building some Gradle plugin that can be applied on any project that can print out the critical path execution time, but it depends upon this. So we are considering open sourcing this critical path visualization, but no updates on this yet. But this is something that we would like to be doing. With that said, the recommendations are this, right? So prioritize modules in critical path, break down modules which are most likely to be present in the critical path, with the modules that take a lot of time executing. And if you have a monolith project, you can start seeing this impact very easily. Just enable org.gradle.parallel is equal to true and start modularizing and see how it affects your build time. And even if you have already modularized project, like very big modularized project, it is worthwhile looking at your critical path metrics to prioritize your efforts, right? Let's say the Santa tracker like had a couple of 5 modules, and you always, the critical path is going to contain any of those 5 modules, right? But when you have thousands of modules and you determine your critical path, and it shows like around 8 or 9 modules there, you know that these modules will give me, if I touch those modules for modularization, it will give me more impact. So that is the summary of this, and we have also talked about a couple of tooling that is available currently. The best tool for that right now is Android Studio's Build Analyzer, which gives you a feedback on how the tasks, apart from critical path or sequential tasks, it also prints out whether if you have an external plugins or something else influencing the build time. It's worth looking into it as well. So that's all I have for today. I want to thank you guys again for joining today, taking time out of your weekend. Please stay safe. We'll spend some time discussing if you have any questions.
Thank you, Arun. Yeah, I have one question. So, converting particular module to pure Kotlin or Java module, will that help reducing build time? Because when you convert a particular module wherein we don't have any Android specific thing,
Yeah.
it will reduce build time in the sense that it doesn't want to spend some time on packaging resources and everything else.
Yeah.
So I think will that be a good strategy?
Yeah, definitely, because like I said, I want to spend more time on this theory bit, but the general recommendation is that we only pull in Android dependency. Like we have two different plugins, right? We have Kotlin Android and we have Kotlin. We only apply the Kotlin Android plugin until unless absolutely necessary. We don't do that. So what do we achieve by that? When you apply less number of plugins, you create less number of tasks, right? So that means your configuration time is going to improve. You basically don't do much work there. So our recommendation is that when pulling out modules, when you look at modules for modularization, we say that look for the utils classes and stuff are very easy to modularize, right? So you'll have like couple of like color utils or data binding utils or dagger utils or some other classes. These are very easy to pull, and when they're pulled, we have a couple of linters saying that blocks the build, saying that if there are any Android, if there are no Android references, then you cannot apply the Kotlin Android plugin. So definitely avoid applying plugins and keep it as lean as possible. That is one of the things that I want to emphasize. And this also helps in configuration time. Does that answer your question?
Yeah, makes sense.
Okay.
I was like, I was not too sure about this, how much it will affect the build time, but this is what something I'm working on. So like I came across somewhere on the internet that if you don't depend on any Android specific thing, then you should consider, converting your module into either Kotlin or Java, whatever you are using. So
Okay.
yeah.
Yeah.
Cool. Guys, any more questions?
Arun?
Hi, Ranjit.
Yeah, hi, Arun. So I want to, I'm not sure if this if this question fits into this context, but do you guys use build source in Grub, and do you think like it affects build times and in any sensation?
Yeah. This is a good question actually. So we did have build source for a couple of internal plugins that we built initially. So we hosted some sources for this plugins and build source folder so that we can apply some linter or any other things. But the build source is a very peculiar thing in Gradle where it always runs before your build, right? So
Right.
for example, if you do simple assemble debug, it is going to check whether your plugin source has changed, and it is going to build and it's going to test, and um, then start your actual build. So your build source, irrespective of whether you're doing some simple executing a test case or something, it is always be executed. So we saw this as a negative. So what we did was we removed build source. We also had a couple of issues with caching. I don't have any references there. It was a while back where when you have a build source, Gradle cache was not always working fine. We did not spend much time investigating this. Considering all these things, and considering the configuration time, what we did was that we moved our plugins to a different folder, and we just pre-compiled them into jars. So we don't on CA or on local, we don't want to be unnecessarily checking the plugin sources if they can be pre-compiled. So in that regard, an official recommendation at Grab is to not use build sources, use pre-compiled things as much as possible. But it really depends upon your metric. I do recognize the balance that we need. So if it is not much of an, for example, if you're only simply using for sharing versions across all the modules, possibly it might not be much trouble on your project size. Yeah, I would suggest do some build scan with Gradle and then see whether you can drop build source or not. Does that answer your question?
Yes, that perfectly makes sense. Thanks.
Yeah. So I have a question from Rohit on incremental annotation processing. So yeah, so annotation basically looking at all the issues online, like reading about Gradle issues, I can say that build authors hate annotation processing because it is definitely a huge impact on annotation processors in general. Is a huge impact on build time because the compile step itself cannot start until the annotation processing is done. Incremental annotation processing can work only when all your processes are actually incremental, right? So, for example, most popular processes like Glide, data binding, Room, Dagger, they adopted incremental processing recently, and Capt also adopted. So, if you're using all those things, it will have a positive impact on your build. However, if any one of them does not support incremental annotation processing, then you're gonna re-execute this incremental step very often. So this will negatively impact build time. But however, if all your annotation processes are incremental, you would definitely see positive improvements there.
Cool. I think then we are done. Arun, if you so if folks wants to ask any more questions, like what's the best way to reach out to you?
Yeah, so Twitter is fine. My mail is fine. I would love to know if you're trying this in your projects and what results you're getting. I would be happy to take this offline and discuss with you and see if I can help in any regard. I'll be sharing this maybe this talk link shortly, slides shortly with Shagar. Is that okay? I can share it with you.
Yeah,
Yeah,
just share with me. Yeah.
yeah. So yeah, you can reach out to me on Twitter or via email. I have left the links in the slides.
All right. Awesome. Cool. Cool. Yeah. So we'll be posting this over YouTube. So maybe in the description section we can include the slides and everything.
Okay.
But yeah, like thank you so much for taking time out and talking about the Gradle thing. So yeah, it was really fun. A lot of information.
Thank
Thank
you.
you so much, and thank you so much, everyone. We will see you in our next one then. Bye and take care.
Okay. Thank you, guys. Bye.